Good morning. I'm Chris Rowan, and I'm going to talk this morning about the interaction among deep learning technology and the silicon universe and startups, to give you some ideas about how some of these new opportunities are creating functionality that we've never seen before, and along the way, transforming much of what we see about the information technology world all the way down to the silicon level. My primary affiliation is Babel Labs, a new deep learning startup. But much of this data comes from my investment and analysis vehicle called Cognite Ventures. So it's really a mix of analytical perspectives and real-world examples from something of a history of technology entrepreneurship and startups. It goes without saying that there is enormous interest, enthusiasm, even hype around the world of AI and deep learning. And to give some idea of it, I captured some hype metrics. You get a page hit on Google on the order of 3 billion. That's enough pages for everyone in the US plus India plus China. So have you read your AI content today? If you look at the startup database, Crunchbase, there are now close to 12,000 startups that say they're doing artificial intelligence. And it captures a very broad range of different technologies, such that the word artificial intelligence appears to have roughly the same meaning as the word new. And if you look at a more technically robust measure of interest, if you look on Archive and you look at how many papers mention neural networks, it's something between 16 and 17,000 papers, roughly, well, most of them published in the last 24 months. So the level of activity by any measure, startups, popular interest, research around AI and deep learning is absolutely phenomenal. In my career, I've never seen the rise of a specific category of techniques and ideas that has been so rapid. It's useful to have a little bit of nomenclature, a little bit of taxonomy to help identify where the biggest opportunities are. We have this very broad domain of artificial intelligence that goes back many decades and includes expert systems and theorem proving and all kinds of artificial reasoning. And within that is the domain of machine learning, of using data sets themselves to fit mathematical models of various kinds that have some cognitive style properties. And ultimately, we have deep learning, which is a particular category of highly complex mathematical models using techniques like convolutional neural networks and recurrent neural networks, which have unusually powerful properties for building models which really do have comparable capabilities and sometimes superhuman capabilities in addressing various kinds of cognitive skills, at least in isolated, well-defined domains. And so we're talking today about deep learning because much of the excitement we find around AI is entirely because of the progress in the last 5 years in deep learning. That so much of what you see in progress in playing Go or computer vision or in speech recognition really is about a revolution in the methods and adoption of deep learning. So when we think about machine learning or deep learning and silicon, there are 3 quite distinct domains that we can address. First, there's the opportunity to use machine learning methods in the classical EDA flows, inside of what we do in simulation and verification and place and route and other chip construction, chip planning methods. And these are typically tasks which are enormously complex, but where having a solution which is statistically close enough is good. So if we want to find better sequences for validation, or we want to summarize circuit models, or we want to do better floor planning or course placement, yield enhancement, are all places where reducing a huge amount of data into useful insights into what to do is powerful. And there's a wonderful effort in CAE ML, which is really thoroughly exploring different ways to use machine learning and deep learning in this. Second, there is the question of, well, how is doing chip design different when the chip you're designing happens to be a deep learning chip? And there I would say, to a first approximation, there aren't major differences between the conventional digital or flow and what you find in other kinds of complex chips. Though it is the case that you tend to have big arithmetic structures, you tend to have lots of closely coupled memories. We are seeing, however, the advent of analog methods for computation in deep learning chips. That people are finding that storing weights in flash cells and doing the multiply and add as a circuit has some interesting promise for high scalability and low energy. But the real opportunity, the thing that is causing the most disruption of the silicon landscape today, is simply the emergence of many, many new designs that include significant deep learning capabilities. And it really reflects the fact that deep learning is a new computational model that sits alongside of conventional algorithmic programming running on conventional microprocessors as an essential building block for these systems. And so we really see this fundamental shift in the nature of software development and the nature of what it means to execute a piece of software, which means we have new types of systems, both in the cloud and at the edge. We see new trade-offs between compute and memory. We see much higher arithmetic density. People now talk about how many hundreds of trillions of multiplies per second are you going to do in a single chip. And there's new room for new arithmetic methods, because often we can do things at low precision. And finally, and this is one of the most intriguing, is there is a real sense in which the neural network is in fact the new circuit. And there's a new category of highly technical EDA-like tools that can be applied to optimization and training and mapping of these neural networks onto whatever the underlying fabric is. Where the fabric is now these arrays of multipliers or arrays of analog circuits or whatever. And so we have these different domains, and we're going to see, I think, moderate impact from the use of machine learning in EDA, very modest impact, small impact in how conventional EDA is different on these chips. But we're going to see an explosion of new kinds of software and new kinds of chips, and that ultimately will percolate down to what are the opportunities seen in EDA. The area, I think, which is going to have the biggest impact is really about vision. Why vision? Well, it's because there's so much data. If you look at what's happening in the volume of image sensors, we're just about reaching a world in which there are 20 billion image sensors out there. And there is an important qualitative change that has occurred in the last year or two as the population of image sensors has exceeded the population of people. In the past, we thought about image sensors as a way to capture images for people to look at and people to share. But we don't have enough people to look at all these images. And so either those images are not going to be captured, they're useless, or there is some amount of automated use or use of some technology to filter those images to find the really good ones. And humans will only ever see the good pictures. And it has some interesting implications about the nature of our computer networks. Because in fact, if you look at where does raw data come from, it comes from sensors more than anything else. And because image sensors are so high bandwidth, they represent virtually all of the data that's being captured. 99% of the data we're capturing is coming from image sensors. And if you take the raw rate, you take those 20 billion sensors, and you assume for the moment that they are on, and you look at what that means we are capable of generating 10 to the 19th pixels per second. And that overwhelms anything we have today or are likely to have in the foreseeable future in network bandwidth, in network storage, and network compute. So we have a really interesting disconnect between the data that we're interested in and our ability to process it. And to make it more vivid, let's look at what a security camera costs. So I went on Amazon last week, and I looked for the cheapest high-resolution security camera I could buy. And that costs me $14. That includes the housing, the power supply, the digital electronics, the LED illumination. It really is a complete subsystem. So if it costs $13.99 today, it's going to cost $10 tomorrow. So I asked the question, well, what does it cost to operate a $10 camera? In different scenarios about where does that image stream go. So we can do a little calculation. So what we find is that you have your $10 camera, and we're going to assume a 3-year lifetime for this camera. And over that time, if it's a really low power camera, it's going to cost us about another $10 to power it for 3 years. And then depending on how we compress that stream, we're going to have very different models of what it costs. So of course I'm at least going to do standard H.4 video compression of this high definition stream. But if I do that and I push it up to the network over a standard DSL or cable wired network, and then I have rolling storage of about a day's worth of video over that 3 years, and then I run a state-of-the-art object detection program. And I've even assumed it gets twice as efficient, and the cost of GPU compute in the cloud goes down by a factor of 2. We're still talking about $8,400 as the cost per camera for that $10 device. And so I really need to think about how I cut down that data rate by selecting the data of interest. If I can do 60x selection, I'm down to a frame per second, and maybe it's affordable to spend $165 over 3 years. But I really have to get down to fractions of a frame per second. That is 1,000x reduction in the data stream before it really becomes something where the mass deployment is reasonable. So it has some specific implications. It says we're going to need to do a lot of semantic compression, which really means something pretty smart. Or I'm going to have completely autonomous systems, and that's reasonable in my car, in my IoT device. There may be a lot of things I do without network interaction on that video stream. And I'm going to see particular classes of applications which really are likely to become quite popular because they can leverage this opportunity to do things locally. So autonomous vehicles and robots, video monitoring of every kind, whether it's home convenience or public safety, and various kinds of user interface and social media applications of video. It also has some interesting implications for where are the smarts going to gravitate to in our network. Because we really have a wide range of choices today about where computing happens. Does it happen right at the sensor? Does it happen on the local area network? Does it happen at the cloud edge? Or does it go all the way up to the cloud? And each of these places has different strengths and weaknesses, especially with respect to deep learning and with respect to high bandwidth data. In general, It's really flexible if you go over here. You have scalable compute, it's pay as you go, you have access to the world's data, you can collaborate and share transparently there. But it's actually really expensive, as you saw before, when you're talking about high bandwidth data. And so, on the other hand, coming over to this end, you have benefits of it being very immediate and local. Once you've paid for that silicon and the power to run it, you're done. You didn't have to pay incrementally for each minute you ran. So we have some clear trade-offs at work. If the computing is done here, it's low latency, it's a much more responsive system. You don't spend seconds in the round trip to the cloud. But if you're really trying to do wide scope of data analysis, you're trying to correlate the data across many streams, then going to the cloud makes sense. If you really care about privacy, the best privacy comes if you don't communicate that at all. It stays local. And the cost in the network, the cost in the cloud compute is real, and it will go up significantly as you push that data up to the cloud. Interestingly, one of the unexpected beneficiaries of all of this algorithm development and all of these new kinds of computing platforms, because of vision, is speech. And in fact, there's a useful analogy that when people look at sound, they see a picture. It's often done at the level of spectrograms, where you really have mapped it into a time and frequency domain, and where a transformation of the speech, the analysis of the speech, the improvement of the speech, can be thought of filtering or object recognition within this image. This is just a classic spectrogram, and this is a noise transformation, a noise reduction, using a neural network. And you can see that I'm picking out the salient features of this speech. These are individual words and phonemes that are picked out of this noisy environment. It's really speech process. It's really vision processing on a sound waveform. And you have, an equally large opportunity. There are 5 billion people out there using phones and radios and other speech-centric devices. Just as there are 20 billion sensors out there, there's about 20 billion microphones. And so things like noise reduction and speech recognition and authentication and synthesis become important. And because it is so important to respect privacy and so important to have short latency, the push for local compute in the speech area is particularly important. And let me give you an example to make it more vivid. So this is a speech enhancement example. Actually, Babel Labs launched this product yesterday. But just to give you an idea of the power of neural network in an area like speech, let's play the first video. Hopefully.
And we're testing our speech enhancement algorithms in the wild, in the middle of traffic. You can see that there's motorcycles, cars, trucks, buses, and right about now we're going to get a lot of noise as the traffic is moving.
Okay, and now the second one. So this is really...
And we're testing our speech enhancement algorithms in the wild, in the middle of traffic. You can see that there's motorcycles, cars, trucks, buses, and right about now we're going to get a lot of noise as the traffic is moving.
So it's speech bleach. And you can't do this with ordinary DSP algorithms. This is just something which you're using the kind of the deep cognitive capabilities of a large complex neural network to get this done. And amazing things happen on a very practical, immediately visceral scale. So the result of all this technical capability is attracting a lot of attention from technologists, a lot of attention from investors, and we're seeing an explosion. You already saw of AI startups, much of which is just riding the wave. But the real power in that wave is, I think, the true deep learning startups. And one of the things that I've done over the last 2 years is evaluate and identify the creme de la creme. About 350 deep learning startups that I think are using the technology in kind of the purest form across a wide range of domains. And it's a really useful tool to understand where is deep learning happening. And so if you look at that, that set of 364 companies, half of them are doing something with vision. 2/3 of them are doing something in the cloud. So the cloud is critically important, partly because it's so easy to get there. One case in point, Babel Labs got its seed funding the first week of January. 25 weeks later, we have a production product running in the cloud. Can't do that, unfortunately, yet with custom silicon. If you look at the embedded world, it's completely dominated by vision. 90% of the embedded startups are doing something associated with vision. Speech is just getting started. It's about an order of magnitude smaller than vision in the deep learning world. And we're seeing a lot of deep learning chip startups. On this list, there are about 25 serious deep learning chip startups, unlike anything that we have seen in the silicon startup world in at least 15 years. So let's look a little bit more about these statistics. Where are they? Not too surprisingly, US is very strong, and if I broke this down on a state basis, 75% in California. The UK and Israel are surprisingly strong. Lots of entrepreneurial spirit. In the case of the UK, lots of early research in deep learning. China is also very strong, though the numbers don't look as big as it feels. And that's because really the cloud is not as obvious or readily accessible domain for startups in China as it is, say, in the US. And so these startups are heavily concentrated in chip startups and embedded vision. They dominate that. So they're small in the total, but if we broke it down to the most silicon relevant applications, China would be significantly bigger, sort of as big or bigger than the UK or Israel in this. And then you have a long tail, where you just don't see very many deep learning startups, for example, in Japan or in continental Europe, not because the technology isn't available, there's lots of research there, but because the startup climate just simply isn't as good as it is in the US, UK, Israel, or China. It's also useful to look at what are they doing. So we have lots of categories here. So deep learning, cloud compute, human-machine interface, security surveillance, audio and speech, medicine, autonomous vehicles, marketing, silicon platforms. And in fact, I've sort of highlighted the ones that feel like they have big volume potential. That is, things that inherently are going to drive silicon. And you can see that in areas like human-machine interface and monitoring and audio and autonomous vehicles and robots and drones, the opportunity for new silicon platforms is pretty abundant. And so one of the questions I get asked all the time is, okay, what's the formula? What do I need to do as a startup to take advantage of this? And I think there are some simple things. And obviously, I'm oversimplifying, but it's still useful. You need to figure out how you're going to get access to a lot of interesting, unique data and to access to the tools. So if you're building a platform or if you're using a platform, data and tools are central. I think increasingly people recognize that you don't just want to build some generic thing and hope people will come. It needs to be about an end application. It's about speech in the car, or it's about vision in smart city, or it's about medical research. I think the task is so embarrassingly parallel that you want to exploit it. And I think the principle of startups, which is get to market quickly, get to market often, change your mind, try a lot of things, is abundantly clear. And then I think you have, kind of the game of pick a technical strategy. Are you working on existing streams? Are you doing a better algorithm? Are you picking out new data? Are you putting sensors in new places to get new data streams? And pick a business model. Is it a cloud XXX as a service? Are you building a system with the sensors, the compute, the software? It's an embedded application, or is it enabling platform? Silicon is usually an enabling platform. Tools are enabling platforms. But you really have a huge range of choices out there. So, in some sense, deep learning silicon is easy. It's this little layer cake, and all you're doing is really spending 90% of your time evaluating a sum of products and a nonlinear function. It's dominated by the multiply add. You have coefficients that, after training, are read-only. They're heavily reused, very regular, static, bounded memory patterns. Programmability helps in terms of making a particular piece of hardware span multiple applications. And there are really robust high-level frameworks to hide the architectural details, which is leading to lots of innovation. But at the same time, deep learning silicon is really hard, because that layer cake is really complicated and deep. You have all sorts of impediments to inefficiency: mixed convolution sizes, nonlinear strides, on-the-fly data reorganization, difficult parallelization of these deep models. And you have various kinds of sparsity. You have memory bandwidth problems, because these really can be large models. And some of the models are not compute bound, they're memory bound. And finally, you need to have very complete software to ease the mapping. So, and in order to get applications really deployed. So we have all of these chip startups happening, but we may actually be getting ahead of the availability of a sufficiently broad set of deployable applications. The Google TPU is a great example. You have this very large systolic array of multipliers, 64,000 multipliers fed by this really intense memory system. And that operates as a closely coupled slave from a conventional processor. Because you spend so much time in this compute, you can have what amounts to a very simple streaming architecture for this. And one of the things we find is that there are architects all over the world who sort of looked at that sum of products and said, oh, is that all it is? I know how to make that run 100x faster. And so I'm listing roughly 30 startups here that all looked at it and said, oh, I can make it run 100x faster. Sometimes they say 1,000x. Now, we'll see how it really plays out. But it's an impressive explosion of innovation taking place there. And why is it? I think we see this fundamental fact that it's a place where you get this huge speed up from having more specialized hardware. And it applies across a very wide range of different applications. The same hardware that runs vision applications really fast also runs audio applications really fast. So it is a general purpose processing method, but where the nature of software is not an algorithm now, it's a learned mathematical function. And so we see interesting things happening in embedded devices, especially in vision and speech. And then in the cloud, we have both training opportunities and application deployment inference opportunities. In fact, if we look at how to sort these guys out, we can sort of scale all those startups across, well, how specialized versus general purpose they are, and how much are they oriented towards low-cost devices or cloud systems. And I've sort of made an attempt to categorize all of them, as well as a few of the standard platforms from Intel and NVIDIA. FPGAs probably sit somewhere near the middle here, depending on which class of high-end to low-cost FPGA you're talking about. But what you see is the biggest cluster is down here in specialized edge devices. But there are a number of companies chasing NVIDIA for the high-end, general-purpose, cloud compute, training domain as well. And so what are the implications? There is certainly the fact this is an essentially new computing model. This is really not a Turing machine. It's a mathematical function which is learned. So you have new kinds of applications, new importance of data set access, because your data is your program, and new kinds of development tools. Hint, this is an EDA-like opportunity in tools. You have this difference between how deep learning runs in the edge versus in the cloud. In the cloud, it's really about training and about inference across aggregated data. It needs to be very versatile. At the edge, it's about high bandwidth, low power, low latency, low cost. Neural networks are inherently diverse. Now, we talk about the highest performance vision ones, but there are many orders of magnitude. I mean, there are interesting things, even in the embedded world, that span over 6 or 7 orders of magnitude of compute level. And so in some applications, especially in vision, for sure you want to think about how you push the hardware to reduce that power. But low-end microcontrollers, existing 32-bit microcontrollers, will run some of these models just fine. And finally, there is this fundamental shift in software methods. And the software methods, over time, the fact that we really have a new thing, like a microprocessor, that coexists with it, but has completely different dynamics of innovation, will have more impact on the silicon economy than the building of new silicon structures themselves. And so we really see that deep learning startups are kind of a window into the future of electronics. And there's lots of resources, like all of this Cognite Ventures stuff is open source, so you can go get the definitive list and all of the details on what they're doing. And there's a nice infographic you can grab at Cognite Ventures as well. So thanks very much. It's an incredibly exciting time because of this radical transformation of at least one dimension of what computing is about. Thank you.